Why didn't you fix it? Okay, I don't care. That's not my problem.
No, wait, that happened yesterday. The door's backwards.
Yeah, so I'm really supposed to pass the law. So
It doesn't.
So you should know all these anyways.
whoa.
A differential equation. A differential equation is an equation that involves a derivative. That order of the differential equation in the order of the highest derivative.
I'm reading.
I'll send them to you on the round. And you know them. I just wanted to review the difference between all the words. So, like when you hear me say differential equation, you're thinking like in algebra where you wanted to solve an equation and use an inverse operation. In calculus, we take an antiderivative. A definite integral has limits of integration. An indefinite integral is the set of all antiderivatives of a function f of x with respect to x. So we denote the difference between them as this. So that's our indefinite. There's no bounds. Its family becomes that capital F of x plus c, where we refer to c as the constant of integration. I just gave you some formulas again. It's helpful to have them. The more you have them, the more you see them, the more you can easily find them. So you have that on like a nice page too with all of them. It's not that bad. It's not. Okay, evaluate the following integral. So you have the integral of x to the negative 3 plus x to the 1/3. So I'm just transforming mine, right? Minus 1 plus e to the 3x. Think of them as 4 separate integrals. Transform it so that it's easier for you to see it. So you get rid of the cube root and turn it to the 1/3. And now you just follow your rules for each one. X to the negative 3 all over x to the 1/3 flip your fraction. You add 1, so 1/3 plus 1 is 4/3. You made me like I was like, what? Okay, and then this is e to the u, right? So again, if you think about the fact your u would be 3x, your du would be 3dx, what do we have to account for then when we take that antiderivative? The e to the 3x simply just needs a divide by 3. And there are no bounds, therefore plus c. That's it. So that is evaluating the integrals when there are no bounds. We'll get to more complicated, don't worry. Okay, so we have the integral. We're just talking again. What's the difference between 3 sine x and the sine of 3x?
Well, the 3 from the first sine x.
Yep, so I would treat this like 3 sine x dx minus.
Maybe we can get divide by 3.
Yep. So again, just think of that as like a mini u sub. So your u is 3x. So your du is going to be a 3dx, so you have to account for that extra 3. Yes.
So, on the inside, if you have like 3x squared,
would you still divide by 3 from that actual thing, or would you divide by like 6x? The derivative of it.
You would have to account for the derivative of it, yes.
You gotta divide by the derivative.
Okay, so just, you get negative cosine x for your antiderivative of sine. Minus, you have to account for that 1/3. Antiderivative of sine is that negative cosine, and this time it would be 3x. Don't forget your constant of integration. Simplify this so it doesn't look like minus signs. You get minus 3 cosine x plus 1/3 cosine 3x plus c. So at the very beginning, I made you review the words differentials and dy's. So if you look at the next example, it's being given to you as a dy dx. So this is where you have to take into account notation. So, and this is where we're going to lead into slope fields and differentials. So that dy dx equals secant squared x plus 2x plus 5. The way it's set up right now, it's not set up really for you to see an integral. In order to integrate, you need that integration dx. So what we have to do is we have to move dx over. So this is where we talk about differentials and we talk about separating our equations. So this is called separation of variables. We're putting the y's on the left and the x's on the right. So we have dy on the left, and we have all the x's. So this is like a form of what? When did we kind of try to separate our dy's and our dx's? And what happened if we couldn't? What was that called? Implicit. Yeah. So this is sort of like a variation of implicit. Currently, the way this is written, dy and dx are together on the left. Now, they're separated. This is called separations of variables. What happens, what is kind of in front of this dy? 1, right? So if I told you to find y, how do I find y? Well, I integrate dy. So what we're going to do is we're going to integrate the left, and we're going to integrate the right. The antiderivative of 1 dy would turn to y. Antiderivative of secant squared. Perfect. Antiderivative of 2x. Antiderivative of 5. And what do I have to tag along? Okay, so this technique that we're talking about, 6.1, it's called solving a differential equation that involves finding a unique equation that satisfies some initial condition. So we kind of hit on this with fundamental theorem of calc. We said, hey, we can find that initial condition. We can find that family of functions. So we're just building and extending on that again. So let's look at an initial condition problem. Given dy dx and a y of 0. So we're going to say that we are given dy dx equals the sine of x. And this occurs when y of 0 equals 2. So again, we've looked at problems like this, except for instead of telling you dy dx, they've pretty much said y equals the sine dx, or they gave it to you a little differently. But again, we are simply applying fundamental theorem of calc again. So what do we want to do? Yep, separate your variables. Integrate those sides separately with respect to the variable. that initial condition. So again, we did this with fundamental theorem. So it's like saying y of 0 equals negative cosine of 0 plus c, all equals 2. So you're kind of solving this part over here. What's the cosine of 0? So you get negative 1 plus c equals 2. So c equals we're going to talk about how we can take these types of functions tomorrow and turn them into slope fields. So 6.1 isn't really necessarily about finding these initial conditions. It's about, can we graph them to make something from that graph? So we'll end there so I can give you your homework. I'll record tomorrow for those of you that are going to be competing, and you have the notes that you need already. They'll be in here.